Okay, so let's get started. Just a recap of last lecture. So on Wednesday, we talk about essentially multiple things. We talk about the role of data and the databases playing in modern data architectures, right? So whenever you are building a website, whenever you are building a mobile app, database and the data are always playing a role. We are hopefully I convince you guys how important data is, how important the database is, and why you should be excited about this course. And we talk a little bit about why do we even want to use a database management system. We talk about different properties that we want to get from a database management system. And we talk about the history and evolution of database management system. We talk about the hierarchical model, we talk about the network model, we talk about relational model. For each one of them, we talk about whether it really satisfies each of those properties that we want. And then we end at relational model, which is one way of modeling and manipulating your data that satisfies all those good properties. And it is also the focus of this whole course. And it is also one of the most popular database systems that you are going to see today. So let's also recap about the properties that we want from a database management system. So the first property that we want is data independence. So what do we mean by that? By data independence, we mean that when you are building one application, you should not really know how data are being stored. Maybe the data are stored row by row, right? Maybe the data are stored column by column, right? But as someone who are building the application, your program should not change when the underlying data format or data layout has been changed. If your database management system satisfies this property, it's going to make your life much, much easier. Because as the data evolve, as the data distribution evolve, hopefully your application do not need to change significantly. And the second property that we want is really to enable declarative efficient data access. So usually when you want to have some queries to ask your database, there may be different ways that this query can be implemented physically. Okay. For example, you want to get information from maybe two tables, right? You can get information from the first table and then get information from the second one. But you can get information from the second one, then get information from the first one. There are so many different ways that you can implement the same query you want to ask to your database. So one good property we want from a database management system is to automatically optimize those implementation for you. We want to make sure you as a user only tell the database at a really high level, declaratively, the type of things that you want to do, defined by certain properties you want the result to hold. In the meantime, the database is going to automatically find optimal or near optimal implementation for your declarative query. That is another thing that we really want to achieve in database. And we want database to have some transactional access property in the sense that even if there are multiple users who are accessing the data at the same time, maybe one user is updating the database, another user is querying the database. We want to make sure both users have the illusion, and that word is going to get really precise down the road. We want each user to have the illusion that only one user is interacting with the database. We want to make sure there's no kind of concurrent conflict between multiple users, even though they are actually accessing data and updating data at exactly the same time. And we want the database to provide a generic abstraction. So we want to make sure the user do not need to worry about all of these above properties for each of the new query. We want to make sure whenever the user are creating a new query, the database automatically deal with all those properties for the user. So these are the four properties we want from database management system. And they are actually the motivation behind a relational database is to try to provide one way to handle your data that satisfy all those properties. So in this lecture, we are going to go deeper into relational model. This is the learning goal that we have today. So we will talk about the relational model, and we are going to talk about how to model your data with relational model. Once your data is modeled in this way, you can manipulate your data by querying it. In this lecture, we are also going to talk about two different ways that you can manipulate your data. You can query your data using relational algebra, which essentially take the view that a query is a whole bunch of set operations. You can also query your data using relational calculus. If you compare these two different ways of querying your data, one of them is imperative, another is declarative. And we are going to put them side by side. And after this lecture, I really hope you to understand the difference between a query language being imperative and a query language being declarative. If you understand all these points, we will have a successful lecture today. Okay, so the structure of this lecture, we are going to define relational model and look at a whole bunch of examples. And then we are going to look at these two different query languages, relational calculus and relational algebra. Okay, so before we model the data, let's try to understand essentially what is data, right? So the most physical view of data is a whole bunch of 0 and 1s stored either in your main memory or stored in your hard drive, right? But when we really talk about it in this course, it actually goes way beyond a sequence of 0 and 1s. Because when we talk about data, it's really the knowledge that we have about this universe. The only reason that data is important is not because they are 0 and 1s, it's because they actually contain all the knowledge that we want to store and all the knowledge that we want to manipulate. So if you take this view, there are essentially two questions that are interesting. The first question is, how can we represent our knowledge? We know a whole bunch of things, right? How can we take a subset of those and how can we represent it in a way that a machine can understand? And the second question is, once we represent our knowledge in a machine readable way, how can we infer new knowledge from the old one? This is also very important, right? If you only store your knowledge but do not generate new ones, one could argue storing them might not be that important, right? So essentially we care about two things. First one, how can we model our knowledge? How can we represent our knowledge? And second, how can we infer new knowledge from old knowledge? So you could have different answers to those questions. And once you have different answers, you are going to have different type of database management system or data systems in general. For example, you could take a very statistical view, right? You can think about your knowledge as some sample from some distribution in the past, and you can treat the inference step of new knowledge as the statistical inference. I find a correlation in my old knowledge, and I try to predict the future. If you take that view, that's going to give you a database system that is driven by machine learning or statistics. In this course, we are going to take a more traditional view. We are going to think about our knowledge as a collection of facts. And then we are going to treat in doing inference, not by taking a statistical view, but taking a mathematical logic view. Essentially, our knowledge is a whole bunch of first-order logic facts that we know is true, in application we want to build. And whenever we say, okay, we want to generate knowledge, what do we mean? We mean that we give the system a whole bunch of logical rules that we also know that should hold in this application. And we hope the database gave us new facts that satisfy all the facts that we already stored in the database, and also this logic rule. This is the view that we are taking when we talk about a relational database. And if you take this view, you are essentially model your data in a relational model. And this will become clear down the road. Okay, so what is a relational model? If you really want to store your data as a whole bunch of facts, right? So there are different ways that you can do it. So in relational model, we take one of the really traditional view that human has been storing fact for thousands of years. That is to store them in a way that look very similar to a table. And this is a table that I don't know how old it is, but definitely more than a couple thousand of years old. And if you look at the structure of this, you can see, okay, so the whole thing is a table. And then I have a whole bunch of columns in the table. Each one of them correspond to one attribute. And if you look at each row of this table, that is actually represent one instance of relationships between different attributes. If you look at most of the tables today, they actually have this type of structure. There's a whole bunch of rows in the table, and there's a whole bunch of columns in the table. Each column is pretty much an attribute. Each row is one instance that's representing the relationship between different attributes. For example, if you give me a whole bunch of students, each student has name, right? Has ID, right? Has which semester you are in, right? Each of this could be one column, one attribute in the table, and each row could be a single student. And if you take one student, you are looking at one specific combination of name, of ID, of each semester they are in. And that is what we mean by each row actually represents relationship between different attributes or columns. So let's make this a little bit more formal. When we talk about the relational model, we talk about two things. We talk about the schema. You can think about it as the header of this table. We want to define what the data looks like before we actually put real data into a table. And we call that schema. A database schema is a set of relation schemas. Essentially, one database contains a whole bunch of relations. And you can think about roughly each relation is like one of this table. And each relation also has its own schema. As part of the relational schema, there's the name of the relation. And also, it contains a set of attributes or fields or columns, depending on how you want to call it, a set of attributes. And each attribute, you can think about it as a column in the table, also has its own schema. It has a name, the name of the column, and also the domain of the column. For example, a column or attribute can be integer, can be string, can be floating point, whatever. But there's a domain associated with each attribute. And if you put them together, right? So what's the database? If you want to define database schema, you need to define a whole bunch of relations. And for each relation, if you want to define a schema, you need to give it a name, and then you need to specify a whole bunch of attributes. And if you want to define the schema for each of the attribute, you need to give it a name, the name of the attribute, and also the associated domain of that attribute. So let's look at one example. This is one schema for one relation called students, okay? And the name of the relation is students. And then we have 5 attributes in this relation. The first attribute is student ID. The second attribute is name, login, age, GPA. All of these are the name of the 5 attributes. And for each attribute, you have the domain. For example, the student ID here has the domain string, meaning that every single piece of data I put into that column or that attribute need to have the type of string, okay? And you have name with type string or domain string, right? You have login string, you have age, integer, you have GPA, floating point. So this is the schema of one relation. And if you want to define the schema for a database, you have a whole bunch of this different schema for different relations. So if you give me this, under the cover, what are you trying to do, right? So essentially, if you give me a schema definition look like this, you are actually, your mental model is that, okay, I kind of want to organize the data that I have into a table that look like this. It's going to be a table with the name students, And it has 5 columns. The first column is called student ID. The second column is called name. The third column is called login. Right? The fourth column is age. The fifth column is GPA. And the first column is always a string, right? So the age column is always an integer. If you define schema like this, essentially you are trying to organize data into a table with a shape like this. So one thing that's to be careful is here we are defining the schema, right? So we are actually not putting the content into this table. We are actually defining what your data look like instead of specifying what your data really is. If you think a relation as a table, here we are actually trying to define the header of the table. That's what we call schema. Okay. So once you define the schema, we can define the instance of a database. And this is when we actually put real data into a database. So a relational instance look like this. If you give me a relation R with n attributes, f1 to fn, and each one of them has domain d1 to dn, okay? So this is what we are trying to say by this notation. I have a relation with name R with n attributes. Each one of this is the name of the attributes. This is domain of the attribute. And we say an instance of this relation is essentially a set of tuples. Essentially, an instance of a relation, IR, like in this case, is a subset of the cross product of all the attribute domain. Okay? If you take one instance in this cross product, that's give you a tuple, right? So you can think about that as one row in the table. And a relation instance, IR, is a subset of this cross product, which means that a relation instance is a set of tuples, and each tuple needs to satisfy the domain constraint specified by the schema. So intuitively, right? So an instance is the content of the table. Okay. And let's look at one example. Assuming we have a relation look like this, with the name students and 5 attributes, right? So this is one relation instance, one instance of this relation. And you can see that there are 3 different tuples in this instance. So the first tuple has student ID equals 0, name equals A, login equals D, age equals 21, GPA equals 3.5, right? And if you look at this, right? So you can see each of this value, like 3.5, satisfy the domain constraint specified in the schema. It is a floating point, okay? That's what we define here. If you look at the age, right? So it's an integer. It's also satisfied the constraint we specified in the schema. So this is one example relation instance. One thing that to keep in mind here is a relation instance is a set of tuples, but not a list of tuples. And that's actually the key difference between a relation and a table. Because when we talk about tables, right? So we somehow have the notion of order between different rows. We have the notion like the first row, the second row, the third row, right? Because they look like a list. Right? But when we talk about relation, if you look at the definition of the relation, this is a set, not a list. In the sense that we do not have any notion of the relative ordering between different tuples. Okay? You could give me one relation where like, if you draw it, like you draw I said equals 0 first, and then you have 1, you have 2. You could give me another relation when you print it, whatever, you have 2 first, and you have 1, you have 0. They are all the same relation instance, because when we define relation instance, there's no ordering between different tuples. And similarly, there's no ordering between different columns. Because when we define the schema, right, it is a set of columns, is a set of tuples instead of a list of tuples, instead of a list of columns. That's very, very important. And here we are talking about relational model. And when you are using a real world database, they are going to have some caveats in the sense that because here we are defining a relation instance as a set of tuples, essentially we do not allow any duplicates. You cannot have two tuples that are exactly the same because otherwise it's not a set anymore. In real world database, you are going to have that in most of the cases. So essentially, in most of the real world database system, they are actually modeling a relation instance as a bag of tuples instead of as a set of tuples. So toward the end of this lecture, we are going to look at the difference between a set and a bag. But when we are talking about the relational model in this course, and also in the exam, we always assume the set semantic for relational model, okay? And that's a small difference between relational model that we are going to define and going to use in this course and the real world database system that you can use in practice. When we talk about the theory side, we always think about the relation as a set. And when we talk about the practical side, that's a bag of tuples. That's one difference that's going to get very clear down the road, okay? Okay, so now we talk about a schema of relation, our database, right? And we talk about the instance of a relation. So there are actually a little bit more concepts that we can look at. So once you have the schema, right? So one thing that we also need to define is the concept of key. So what do we mean by that? So we first have the concept of candidate key. A candidate key of a relation is a minimal set of fields that identify each tuple uniquely, okay? So which means that if you give me a relation with maybe n different attributes, if I know the value of a subset of the attribute, I can uniquely identify a tuple. If this is true, we mean that we call that subset a candidate key. One example is think about the student table. I have student ID, right? If in my application, every single student has a unique ID, it means that if I know the value of student ID, I could uniquely identify a single tuple corresponding to a single student in my application uniquely. There doesn't exist two students with the same ID. In this case, we will call the student ID a candidate key. And there could be a whole bunch of candidate keys in a relation. And we will pick one and call it primary key, okay? And when we write the schema, we are going to write in a way by underlying the corresponding attributes. In relational model, every single relation must have a key. This is always possible because we are modeling the relation as a set. In the worst case, the whole set of attributes is one key. So key always exists in relational model. And whenever you are defining the schema of relation, you need to define your primary key, which is one of the candidate key that you pick. So let's look at this example, right? So our student table. Again, the name of the relation, students, 5 attributes, each attribute have their own domain. So here you see there's underline, right? So in the kind of SID kind of attribute, which means that we pick SID as my primary key, which means that in my application, if you give me the value of SID, I can uniquely identify one tuple in the student table. There doesn't exist two students in this table share the same SID value. That's what I mean, okay? By assigning SID as the key. So if you think about what candidate key or primary key is doing, they are really trying to define for you what is a valid instance. Because once you define the key, you cannot really put whatever tuple you want into a table, because some of that will violate the key constraint. So let's look at this example. This is a valid instance for this relation. Why? Because of two reasons. First, every single tuple satisfies the constraint specified by the domain. Okay, if I take every single tuple, the age attribute is always an integer, the GPA attribute is always a floating point, right? So name and login is always string that are consistent with the domain of each attribute I specified in my schema. This is the first reason. And second reason is that this instance actually satisfies the key constraint. If you look at the schema, the primary key in this relation is student ID, which means that if I know the value of student ID, right, I could uniquely identify a tuple in this instance. Which means that if you give me two tuples, any of the two tuples, I cannot have the case where two different students share the same student ID. And you can actually check whether this property hold in this instance. And in this case, it actually satisfies both the domain constraint and also the key constraint. And that is why this instance is a valid instance for this relation. This is another example that the instance being not valid. Okay, so this is one invalid instance of this relation. If you think about why, you first check whether the domain constraint is being satisfied. In this case, yes. If you look at the value in every single column, they satisfy the type that you specify in your schema. However, if you look at these two rows, they actually violate the key constraint. Why? Because I have two different tuples share the same value of student ID. And because student ID is my primary key, it means that if I know the value of student ID, I should be able to identify a single tuple. But in this case, because of your data, I cannot do that, right? So knowing student ID equals 0 doesn't bring me to a unique tuple or unique student in this case. And that violates the key constraint that I specified in my schema. So we can make this more formal. If you give me a relation look like this with the name R and 3 attributes, I have K, I have A, I have B. And if I say, okay, so my primary key is K, that single column, this actually defines all the possible valid instance I could put in this relation. Essentially, all the valid instance should satisfy two constraints. One is the constraint specified by the domain. It needs to be a tuple of this type, okay? And need to satisfy the constraint specified by the key constraint, right? Which means that if you give me two tuples in this instance, KAB, K prime, A prime, B prime, in this instance, and if they share the same key value, K equals K prime, it should imply that AB and A prime, B prime should be the same, which is a formal way to say, if I know the value of K, I can uniquely identify a tuple. If my instance satisfies this property, it is a valid database instance for this relation, okay? And down the road, you are going to see a whole bunch of different ways that you can specify constraints. We talk about the type constraint, right? So we talk about key constraints. There are a whole bunch of other type of constraints that you can do in database. But what data is trying to do is once you define the schema, and then you give me your data. If your data doesn't satisfy all the constraints, I'm going to reject you. I'm going to say, okay, you are violating the constraint that you want. I'm not going to put this data into the database. Okay, so this is going to be very useful when you want to ensure the integrity of your application and the integrity of your data. And down the road, we are going to learn a whole bunch of different ways to deal with that. And here we are looking at the most simple way of defining probably the most simple type of constraints: domain constraint, key constraint. Okay. Just to recap, we define what is a schema of relation. Has a name, has a set of attributes. Each attribute has a domain, right? And each relation schema need to also specify the primary key. Okay. once you have a schema, inherently you are defining all the possible valid instances. They need to be the instance that satisfy all those constraints. Okay. So now let's look at some examples. So assuming that we want to design a database to store information for a university. So what type of data do we have? Right. So we have professors. Right? Each professor has the personnel number, has name, has level, has office. Right? And we have students, and we have lectures, and some lectures have prerequisites. Right? You need to take one lecture in order to take the other one. There's a dependency between different lectures. And students attend lecture. And some students also take tests in lectures, and he or she going to get a grade. So assuming this is all the information that we want to model, we want to store in our university database, how can we store all the information or model all those information using a relational model? So there are multiple questions here. The first one is how to design the schema. And second is what are the valid instance that I could put into a database with that schema? And we are going to use the example to try to think about these two questions. So let's try to model the information we have about professors. Okay. So here, one way to do that, and there could be different ways, right? But one way to do it is to create one relation called professor. Here, the professor is the name of the relation. And then I have a set of attributes associated with each professor. If you think about there's a professor table, right? Here I'm trying to define different columns of that table. And each row in the table will be a professor. I have a personnel number, which is an integer, right? And I have the name of the professor, which is string. I have a level, I have office. I have a relation with 4 attributes. And here I have my primary key as personnel number, because if you tell me the personnel number of professor, I should be able to uniquely identify a single row in your table. I do not want to have a database where 2 of my professors share the same personnel number. That confuses everyone. Okay. So a more compact way of writing this is to say, okay, I have professor relation. I have the first attribute is primary key because it's underlined with a type integer. And then I have attribute name, string, level, string, room, integer. Okay, it's clear. So the instance of this relation is a set of tuples. And each tuple will have the shape look like this. It will have a personnel number, the name, the level, the room. And this is one example, okay? And here you can see we have 3 different tuples in this instance. And one tuple with personnel number 2125, here's the name, here's the level, here's the room. It satisfies the domain constraint, so we are happy. And we also need to check whether it satisfies the key constraint, right? So in this case, it's fun because if I know the value of the personnel number, I can uniquely identify one tuple, right? So it doesn't exist the case that 2 different rows share the same value in personnel number. That's my primary key. So this is one example that for instance that violate your key constraint, right? So as you can see, I have 2 professors, right? John and David. Both of them share the same personnel number like value, okay? So this violates my key constraint. So if you try to put the second instance into your database, you are going to get error, right? So this is actually a simple example about how to model essentially professor information using relational model. And we can continue this exercise, right? So one thing that's very similar, we are going to go a little bit quicker here, is for student. So the schema here is, okay, so I have the relation with the name student. I have one attribute, which is personnel number. I have a name, I have semester, I have this. And the instance of this relation will be the set of tuples, and each tuple has 3 attributes. And this is one example of a valid instance. Why is this valid? Because first, it satisfies the domain constraint, and second, it satisfies the key constraint. This is one example of an instance that's not valid. This could get a little bit trickier compared with our previous example, right? So here, if you think about what's the problem here, it's actually not that it violates the key constraint, because if I know the value of this personnel number, that still bring me to the same tuple, right? If you look at these 2 tuples sharing the same personnel number, they have the same name, they have the same semester, it's the same person, right? So the problem of this is in relational model, we are modeling an instance as a set. You cannot give me a set with duplicate information, then that's not a set, then that become a bag, okay? So the problem of this instance is actually not a set, okay? So we can do the similar exercise for lectures, right? So let's go a little bit quicker here. So we can have the lecture relation with lecture ID, with title, with credit point, with which professor is teaching it. Okay, so we have the professor number, which you can store the professor ID, right? Professor's personnel number here. And we have this. And instead of this will be a table that looks like this, right? So my primary key is my lecture ID. This instance satisfies both the domain constraint and the key constraint. And similarly, you can have the instance that look like this. So if you look at this example, right? So we put it here for a reason. This example might look a little bit weird, right? Because if you think about what this instance really tells you, this instance actually tells you that I have the database course appearing twice. They have different ID. I have one database course with 4 credit points taught by Professor 2125 with lecture ID 5001. I have another database course with the same credit point taught by the same professor with a different lecture ID. In your world, in your application, that might look a little bit weird, okay? Maybe you think, how could that be possible? But based on the model of your data, which is a schema that is defined by you, this instance is a valid instance because it satisfies domain constraint, it satisfies the key constraint. If you do not want this instance to be valid, you need to twist your schema, okay? But once you define the schema, it's actually, if you think about what schema is trying to do, schema is your way to kind of express your assumption on the application or on the data. Given the assumption you have, this instance is valid. Maybe there's a gap between what is possible in your data model and what is possible in real world. If that gap really matters to you, you should twist your schema design, okay? To make sure you really reflect kind of the property of the real world application you want to model, okay? But if you give me the relational schema like this, the second instance is valid. There's no problem with that, okay? So we can kind of keep doing this exercise. If you want to model the kind of the relationship between different lectures, for example, some lecture are the prerequisite of other lecture, you need to take lecture 1 before you take lecture 2. You could have one relation called requires, and just store essentially 2 lectures, right? You have prerequisite, you have follow-up. And both of them are integers because we have the lecture ID in the lecture relation as integers. So once it becomes a little bit interesting is if you think about how can I define the key here, right? So what is my primary key of this relation? And that become interesting. And we can look at different options, and we can look at what type of instance it is valid under each of these options. Option 1 is I have prerequisite as a primary key. Option 2, I have follow-up as my primary key. Option 3, I have the combination, okay, of prerequisite and follow-up as my primary key. I have only 2 attributes, so I only have these 3 options. Right? if you want to say, yeah, so like, yeah, because like primary key need to be a subset, non-empty subset of the set of attributes. So to understand the difference between these three different options, we can look at what type of instance are allowed under each of the option. Because that's what really you are trying to do by specify primary key. You are trying to say, kind of try to specify the subset of instances that are valid and the subset of instances that are not valid. That's fundamentally what you are trying to do. So let's look at this instance. Okay, I have prerequisite 5001. I have follow-up 5041, 5043, which means that if I take, so to take 5041, I need to take 5001. If I want to take 5043, I need to take 5001, which is a reasonable kind of instance, right? So yeah, so if you are building a university, I would think this one's fine, right? So let's think about whether this is allowed under each of those options. For option 1, this is actually not a valid instance. If you have prerequisite as the key, this instance is not valid, right? Because I have two tuples sharing the same value here. So this instance is actually not valid under option 1. If you really want to allow this instance in your application, then option 1 is not really a good choice because it's going to reject instance like this. And if you look at option 2, it's actually okay, right? Because if I have follow-up as my primary key, which means that I cannot have two tuples sharing the same follow-up value, this is fine, right? And similarly for option 3, it is also fine. If you look at option 3, it is essentially okay. I have this combination as a primary key, which means that I cannot have two tuples sharing the same value on this combination. I cannot have two tuples that has the same value on prerequisite and have the same value on follow-up. Okay, that's what we mean by having a combination here, by having a set of attributes or key. So this is valid under option 2 and option 3, but not valid under option 1. And let's look at this instance. Okay, this instance essentially, okay, I have one follow-up course 5041. To take that course, you need to take two different courses. You need to take both 5001 and 5002. So this instance is valid under option 1 if you have prerequisite as a key, okay? Because you take these two tuples, right, they have different values on the prerequisite, right? However, it's not valid under option 2, right? Because these two tuples share the same value on follow-up. If my primary key is follow-up, then I do not allow instance like this. And also they are valid under option 3, right? Because if you take the combination, right, I cannot find two tuples that share the same value like both in these two columns. So if you are building applications, right, so what you are really thinking about is whether my data model reflect my reality, right? So I think a reasonable person would say both of these two instances are reasonable in the real world. If I'm building a university database, I would allow both, right? So in this case, when you try to design the schema of your relational model to model your data, option 3 seems to be a more reasonable choice, right? Because that is going to allow kind of these two different cases. Okay, so we can also model information about students taking lectures, right? So this is going to be very similar. You have the personnel number of the students, right? So you have the lecture ID, right? So here you can do the same exercise as which of the attribute or which set of the attributes, subset of attributes are primary key, right? So you can, when you go home, right? So you can actually look at essentially these three different options and try to think about what type of instance they are allowing or which type of instance they are rejecting, right? So, and here, if you go through the same exercise, I think we are going to reach a similar conclusion. That is a reasonable design of the schema for many cases would have the primary key as a combination of the student ID, the personnel number, and also the lecture ID. Because that would allow one student to take multiple courses and also one course to be taken by multiple students. Right? So if you do option 1 on option 2, you are actually rejecting one of those cases. And you end up have one course with only one student, or you have one student can only take one course, right? So that's not really that reasonable in many of the applications that we are looking at. That would be a very weird university to attend. Right? So yeah, so you can have students take tests, right? So here is very similar, right? So you have personnel number of the students, you have the lecture ID, and you have the grade, right? You could have the key as the combination of personnel number of the students and also lecture ID. So what's the implication of this? So implication of this is that a student only take exam of a lecture once, okay? Why? Because otherwise you are going to have essentially kind of like two tuples, right? With the same student, same lecture, different grade, okay? It's going to violate our key constraint, okay? So this is the underlying assumption that we have. If your application doesn't satisfy this assumption, for example, if you are running a university, which is also a very reasonable one, right? So that one student can take exam of one lecture multiple times, right? Then you need to redesign the schema by specifying a different key constraint, okay? Whenever we are specifying a key constraint, we are not saying what is right, what is wrong. We are simply exposing our assumption on the application. If you don't like the assumption, then change your key constraint, okay? So that's all for the first half of the lecture. When we get back, we are going to talk about how to query the data that is already being modeled using a relational model. And if you have any questions, just speak up. I think there's too many chat messages. It's very hard for me to go through all of them. Just unmute yourself or raise your hand. I'll be here to answer your questions, okay?
Yeah, I have one question.
Yeah.
So I wanted to ask, you said that the order of the set of tuples doesn't matter in a relation instance, and it shouldn't matter.
Yes.
What about the order of the set of fields in a tuple? Does it need to be ordered in the way that we have ordered the attributes in the header, or can it be in any order when we, for example, query the data?
That's a very good question. So in this course, the order of the attribute doesn't matter. You can order attributes in whatever way. So it's a set of attributes.
Important for the for databases in general, or is it?
I mean, that depends, right? So depends on so this is actually very interesting. If you go deep into database theory, which we will not cover like in this course, there's always two ways to represent a relation. You can represent as a kind of as a list of attribute. You can identify every single attribute as a position, like the first one, second one, third one. You can build a database theory over that. Or you can say, okay, so a relation is a set of attributes. Each attribute is specified by the name, not the position. Then you have a different way of writing down your database theory. So in this course, we model relation as a set of attributes, and therefore the order doesn't really matter for us on the theory side. On the system side, it could be interesting because we are going to see actually after Easter when you build a real database system, you need to store the relation in some way, right? And if you are having the raw store kind of database, the order of the attributes actually reflect how you store the relation on your hard drive. So it has some of the performance implication. So it's not 100% independent, right? But the goal of the database is to make sure that doesn't really matter as a user in most of the cases, right? So just to answer your question, on the theory side, when we talk about this relation in an abstract way, a relation contains a set of attributes. The order doesn't matter at all. But you are using a database in practice, sometimes it has a difference, but that's a practical one, not a theoretical one. So does that answer your question?
Yes, thank you very much.
Sure. Yeah, Daniel, I think our next one.
Yeah, it's a it's a follow-up question to this.
Yeah.
So we're saying that the attributes are a set, but didn't we just define them as a tuple or tuple? Or is it something like we're saying that like here we say PLG1 and we define the primary key and everything together as a tuple. So
oh yes, yes. Yes. Oh, okay. So that's a very nice catch. So here I'm just yeah. So here is just I'm abusing the notation to do not write the name of the attributes. So the right way to write this will be personnel number equals to P, lecture ID equals to L, grade equals to G1.
Oh, okay. Okay.
Yeah, but that's simply too long. So I'm abusing the notation a little bit to specify the tuple. Yeah, but that's a very good question. Yeah. Okay, cool. Yeah, you guys can just unmute yourself. Yeah, first come, first serve. Yeah.
I wanted to ask a question that was asked in the chat.
Yeah.
Not by me, but I'm interested in the question. So what exactly is a relation? Because we are differentiating between relation and schema. So what is the difference there?
Okay, so a relation, so it's an abstract concept that it has a schema and also it's okay. So when we talk, yeah, let me think of. Okay, so when we talk about, okay, so when we just say the word relation, so it is ambiguous because we don't know whether you are talking about the schema of the relation or whether you are talking about the relation instance, right? So so first one, like, is the difference between a relation schema and a relation instance clear?
No, so what is the difference between a relation and a schema?
Oh no, so like, is the difference between relation schema and relation instance, is this two concept clear? Yeah.
Yeah, this is clear.
Yeah, so when we say a relation, sometimes you really need to kind of decide what that means using the context. Sometimes people mean the schema, sometimes people mean the instance.
Okay.
Yeah, so that really depends on the context of like what the like what you mean by I mean so when you read the book, when you read the papers, sometimes when people say relation, when it is clear, it is relation instance. Sometimes when people say relation, it means relation schema. So in most of the cases, it should be very clear from the context. Yeah.
And for example, on this slide, you're writing relation tests and then schema. And
Oh
you
yeah,
write
so
schema.
yeah. So here I mean the schema of the yeah.
Thank you.
Yeah.
So, hello.
Hello. Yeah.
Okay, I was just not sure. So, just a follow-up question to that one. So, basically, the word relation is kind of pointless, and it's just for the sake of laziness.
So what do you mean? So, sorry.
So the word relation, right? Because
Yeah.
you said like sometimes it's used for this, sometimes it's used for that, but in the end, there's no clear definition for it. So it's just like you can just use it however you want, but you need to kind of specify by context what you mean.
Yes. So when we talk about relation, it could mean the schema, it could mean the instance. So I'm sure one of that is abusing the definition, right? So if you ask me, I would say the word relation always means schema. But people use it in different ways. So do not be surprised when you read a paper, read a book, when they say relation, they actually mean the instance.
All right, thank you.
Yeah. So if you ask me, right? So my personal opinion is relation always means schema. When you say the content of the instance, it should be called relation instance. But that's me. That's my personal opinion, right? In reality, when you read the book, read the papers, I just don't want you to be confused to say, yeah, they are clearly talking about instance, but they are using the name relation. Why, right? So you are going to see people use it in different way in practice. But if you ask me, personally, I believe relation should mean schema, right? But yeah,
I mean,
in practice, my opinion doesn't matter that much, right? So you are going to see different use case of this word, right? Yeah.
Sure. I was reading the book yesterday and I was a bit confused by that whole relation definition because they somewhat said, if I remember correctly, a schema defines a relation. So I knew it was like, so, but an instance of a relation is like the actual set of data, and then it was very confusing what it actually was. And nowhere in the book they actually said, hey, a relation is this. They just said a scheme is this, instance is this, but yeah.
Yes,
Thank you
yeah.
for the
So
answer.
I mean, yeah. So that's exactly what I mean, right? So when you read a book, when you read and also that book is a very good book. So you are going to see more confusing use case of these two words in other books and other papers.
That
Okay.
sounds great. I'm looking forward to it. No, I mean,
Yeah. So
the book is
so
good.
like
The book is
yeah.
good.
So
I like it.
yeah. So don't be confused when you see a paper when people use this word just for the instance. Yeah. That happen a lot. Yeah.
Sure.
Like especially when you are like talking about those like database in practice, you say, so here's my relation, right? So then clearly they mean the content itself, right? Yeah, but this difference will not matter too much down the road. Yeah, like because in most of the cases, it's going to be very clear whether it is a piece, whether it is a schema or whether it is the instance. Yeah.
I think for me, it was more fundamental, like trying to fundamentally understand everything so it makes sense. That's why I asked that before in the chat. Anyway,
Yeah.
Thank you for answering the question. I appreciate it.
Sure.
Could I ask another question about the keys?
Sure.
So you said that the key is something that uniquely identifies any tuple. What happens if we have more than one good option for what the key might be? Do we then just select one of them arbitrarily, or is there some other way to select it? Or I mean, is it something that depends only on the person who creates the database?
Yes, right. So like to some extent, the schema is whatever you as people decide in the database decide what the key is. That's what the key is, right? Whether and you don't need to have the key reflect the reality, right? So, but in practice, when you have a relation with two candidate key, the question is how can you pick the best one? So there's a whole bunch of rule of thumb that you can follow that we are going to talk about, I think, in maybe 5 or 6 lectures. Right, so there's something that's clear. For example, hypothetically, right? So you do not want the key to change a lot, right? So as a very extreme example, you are building the professor table. There are 2 columns, right? So one is the professor ID, and second, which could be the key. Another could be the current location of a professor, right? Both are keys, right? Because professors don't overlap, right? So, but however you want to use the professor, maybe hopefully you want to use professor ID as a key, right? Because the location of professor will keep changing. It is still key, but keep changing, right? So that's going to make the database a little bit hard to build. So there's a rule of thumb about how to pick one key over the other as a primary key. But at the end, you as the person who built the database should decide what's best for your application and what makes sense for your application. Right? So that answer your question.
Yes, thank you very much.
Cool. Okay, so let's continue, right? So what have been doing over the first half of the lecture, right? We talk about relational model, we define it, and we show actually some examples about how to model your data using relational model. Yeah, so this is actually one possible design of the schema for our university example, right? So we have a whole bunch of relations, and this is one example instance of this database. So there are multiple things we need to keep in mind. So first one is there are multiple ways to design a schema. Given one applications, you can define a whole bunch of different type of schemas. Just like for one relation, right? So you can have different choice of keys. There could be multiple candidate keys. You can pick one or the other. And later down the road, you are going to see kind of more complex case. You can normalize the relation or not, right? A whole bunch of decisions you can do when you design the schema. So different designs may have different pros and cons, both in terms of data redundancy, but also the performance, right? So what they are trying to really optimize for. And we will see how to design a good schema later in the course when we talk about the database design theory. Okay. So now we design relational model. We kind of have a model for our data. We kind of know what it is. It's a whole bunch of, if you talk about database instance, it's a whole bunch of relation instance, right? Each one of them is a subset of tuples, right? And then the question is, how can we get information out of my data? How can I get insight out of my data? So here we are going to talk about the process of querying your data. So what is a query? A query is a function that takes as input a database instance, which is a set of relation instances. You can think about intuitively as a collection of tables, and output a new relation. Okay? So that's a function. It's a queue, it's a function. Input is a whole bunch of relation instance. Output is a new relation instance. And the query language consists of a set of functions that you can express in that language. Okay. So now let's look at one query language, like one way to query your data, and that is just by using something we call relational algebra. So this is actually an imperative way for you to query the database. The meaning of the word imperative is going to become very clear at the end of the lecture. Okay, it means that when you query the database, you actually tell the database how to run your query to get the information that you want. So the opposite of that is a declarative query language, in which you tell the database the property of the result you want, but do not tell the database how to get there. So that's a key difference. So when we look at these two query languages side by side, that's going to become very, very clear. Okay. So here the head of idea is very simple. So relation instances are sets, they are set of tuples. If you want to get information out of this, we can use a whole bunch of set operations. That seems to be a very natural choice. Right? You can have the union of the relation, you have difference, you can do selection, you can do projection, you can do cross product, you can do renaming, you can do join. We are going to go through each of this one by one, but from a fundamental level, because relation instances are sets, we should be able to do a whole bunch of set operations over them to get new information. Right? So that's a high level idea. Right? So let's look at one operator, right? The union. Right? So if you want to calculate the union between two relations, R1 and R2, right? So X is in the result if and only if either X is in R1 or X is in R2, right? So that's the definition of this. If you say, okay, so I have relation R1, relation instance R2, I do R1 union R2, right? So here is the definition about what should be in the result. And as you can see, it's a very natural definition, right? So as one example here, assuming that we have three relations containing different products, product 1, product 2, product 3, three different relations. If you do the union between product 1 and product 2, you are going to end up with three tuples. The first tuple comes from product 1, and the second and the third tuple come from product 2, right? So as you can see, this is a query, right? So this thing, product 1 in product 2, is a function. It takes as input a whole bunch of relation instances I have in my database and give me a new relation. Okay. So similarly, you can do difference, right? You can do R1 minus R2, right? In this very natural way. If I do, for example, product 2 minus product 3, what do I get? I only get this tuple, right? Because like this tuple, the first tuple in product 2 and the first tuple in product 3 is kind of canceled out, right? So I end up having something like this. Again, this is another way for you to take the information you have in your database and generate new information, right? So again, right? So it's very natural to say that if the schema of two relations doesn't match, right? For example, you have one relation with 4 attributes, you have another relation with 3 attributes, you cannot do union, you cannot do difference, right? For a very clear reason, right? So for example, I have two relations, R with PID and name, I have S with PID and title. I don't know how to union them, okay? Because the name doesn't match. I don't know how to compare tuples here. On the other hand, okay, because relations, the attributes are set, okay? Like even if the ID doesn't match, so like even if the order I'm writing it down doesn't match, you can still kind of like do set operations. For example, if I have a relation R with PID and name, I have S, name, PID, and I just write them in different order, but because they are sets, their order doesn't really matter. Okay, so you can still union these two. This is okay. And this is within the framework of relational model. When you are using a real database, we are going to talk about it. Okay, that's going to be a little bit different. Yeah. But when we talk about theorem and talk about relational model, attributes are sets. Okay, you can do intersection between two relations, right, in a very similar way, right? And you actually do not need to implement the intersection, right? Because you can use the set difference to represent it, right? So for example, here, if I'm doing the intersection between product 2 and product 3, right? So I end up with one tuple, right? And then I can do selection of tuples. So the semantic of this operator is you return tuples which satisfy a given condition. So what do I mean by that? To specify a selection operation, I need to have one condition called C, okay? And then this is actually another relation. So one tuple is in the result, if and only if, first one, this tuple is in the original relation R, and second, this condition need to be true, okay? So let's look at one concrete example. If I have a query that looks like this, it's a selection operation with condition price larger than 1 to 5, and select over product 2. You have this, what will be the result, right? So I'm going to look at every single tuple in this relation, product 2. I'm going to check whether the condition is true or not. For the first tuple, the condition is not true. For the second tuple, the condition is true. So in the result, I will only have the second tuple. Okay, it's simple, right? Similarly, I can do different type of conditions. I can sub-select the name, right? In this case, very naturally, I will have the first tuple because of the name. And I can do kind of conjunction or disjunction, whatever you want to do on the conditions, right? So here I have the name equals to this and price larger than this, right? If I check every single tuple in product 2, I find nothing. So here what am I going to get? I'm going to give you an empty set. I'm going to give the relation instance with no tuple. That's still a valid instance because I never say relation instance need to be non-empty. Okay, so but here if there's no tuple matching your condition, you are going to give me something that is one relation instance, still a relation instance, but it's empty. It's empty set. Empty set is still set. Okay. In this example, you are going to give me something empty. Okay, but you are still going to give me something, okay? And that's in still a relation instance. That's very important. You can do projections. Okay, so by doing projection, you are actually only keep a subset of the attributes. So here's one example. I'm taking the relation product 2. I want to only keep the PID column and I want to keep the name column. I want to get rid of the price column. Okay, so I can simply do a projection onto PID and name over product 2. And then I'm getting a relation that's kind of thinner because you are getting rid of one of the attributes. And then I have the same tuples, right? For every single tuple, if it appears in the input, it also appears in the output, but you just get rid of one of the attributes. So here I intentionally write PID equals 2 before PID equals 1 to re-emphasize the point that relations are set. There's no ordering. Okay, I can order BlackBerry over Android. I can order Android over like BlackBerry. It doesn't really matter. The order between tuple doesn't matter. The order between attribute doesn't matter. Okay. So it gets more interesting. You can actually do this set operation over multiple relations. So for example, in this case, I can do the cross product between two relations. You have the customer, you have the purchase, right? These two relation instance. I can actually do the cross product. So this is a formal semantic, but intuitively, it just gets one tuple from relation 1, get another tuple from relation 2, and put them together as a new tuple, right? So if you do the cross product between customer and purchase in this example, I have 3 customers, I have 2 purchases, right? So I'm going to end up with essentially 6 tuples, okay? So here's color coded, so it should be very easy to see. For the first tuple of purchase, I have all the tuples from customer. For the second tuple of the purchase, I have all the tuple from customer, okay? As you can see, it's going to get very large, right? If I have 1,000 tuples in the first relation, you have another 1,000 tuple in the second relation. If I do the cross product, I'm going to have 1 million tuple in the end. That is why it's very rare in practice. But it's going to be very useful for you to express different type of joins. Okay. So one thing that's interesting to say, okay, so now I have output relation. What is the key, right? So the output, so the key of the output relation will be the combination of the key of the input relation. Okay, so which is kind of very, very clear, right? Because when I do the cross product, I essentially have kind of duplication of information. So the CID here is not the key anymore because I'm actually repeating like them multiple times, right? So the only possible key for your output is you take the key of relation 1 and you take the key of relation 2 and you put them together. Okay. And then you can do renaming of your attributes. For example, so you have a kind of one relation, right, with n different attributes. I can simply change their name. Okay. So for example, if I have something like this, you have the purchase. Okay. If I rename it to ABC, right, which means that I'm going to have a new relation, okay, with the same content, but simply different name of the attributes. Okay. And only the name of the attribute change. And if you think about, okay, why do we even need this, right? So that's going to be useful. For example, if you do the cross product between customer and purchase, right? You can see the name CID appear in both relations. After the cross product, I need some way to distinguish like these two different columns, whether it comes from the customer or whether it comes from the purchase, right? So therefore, I need actually to rename one of them before I do the cross product, right? So otherwise, I'm going to have two attributes the same name, which is not really allowed in your original model. So that's why we cannot need this. Okay. And now it gets into some more interesting operators. One operator that is actually one of the most frequently used operator down the road when we talk about database is natural join. And it actually applies to two relations with a shared attribute. Okay, so here you have one relation R1 with two attributes A and B. You have another relation R2 with two attributes B and C. If you do the natural join between these two relations, this expression is essentially what we are trying to do. Okay, essentially, mathematically, it's first do the cross product between R1 and R2, and it select all those tuples in the cross product with matching value on the B attributes. And then it's projected to A, B, and C by kind of eliminating the duplicates on the B attributes. Essentially, intuitively, it is to say, I go through every single tuple in R1. And for every single tuple there, I try to find another tuple in R2 with the same value on B and bring that to me and put that in the result of my join, of my natural join. So if you look at this, right, so it's usually proceed in two steps. You have a selection step. They check equality on all the common attributes between these two relations. And then it's do the projection to eliminate duplicate common attributes. So let's look at one example, okay? So I have the customer relation here, and I have the purchase relation here. So they share the same attribute, customer ID, okay? So if you do the natural join, so what you actually have is going to be something like this. So let's look at why it is the case. Essentially for customer 1, with customer ID equals 0, I'm going to look for tuples in purchase with the same customer ID. Here, I'm going to get it. I'm going to find it. I'm going to find this tuple, the orange tuple, going to match the like first tuple in customer. So I have this 0, John Zurich, 0, A. This one, it comes from here. The first tuple comes from here. Okay, makes sense? And then I go to the second tuple here, and I try to find another tuple in the purchase relation sharing the same value on customer ID. Here, I'm also going to find it, right? So that's a blue tuple, right? They share the same customer ID equals 1, right? And then I go to the third tuple, say, so is there any purchase tuple in the purchase relation with CID equals 2? I cannot find it, so it's not going to be in the result. Okay. So intuitively, right, if you have one relation, customer, store all the customer relations, and you have another relation called the purchase, store the information about which customer purchases which product. If you do the natural join between customer and purchase, intuitively, you are trying to find essentially which customer purchases which product, right? So, and then you can actually put a whole bunch of natural join together. Okay, you have another kind of, if I not have another product table contains the detailed information of each product, right? You can do a natural join like this, and you are going to get something like this. Essentially, for every single PID, right? You are going to get the detailed information from product by matching their PID in the product table. And the natural join is interesting. And also there are multiple corner cases. So let's think about this case. I have two relations. I have R with three attributes, A, B, and C. And I have S with two attributes, D and E. There's no shared attributes by name, okay? And then if I want to do the natural join, right, between R and S, so what do I get? I essentially get a cross product between R and S, okay? If you think about why, it is because then the subselection part will filter out nothing, right? And another corner case is, what if I have two relations? I have R with attributes A, B, and C, and I have S with attributes A, B, and C, meaning that they share all the attributes by name, right? If I do the natural join between R and S, I'm essentially going to get intersection between R and S. And if you think about why, right? So essentially, I can only get those tuples that appear both in R and S, right? Otherwise, they will not appear in the result after the selection. Right? Make sense? Okay, so natural join is just a kind of a very natural way to define the subselection condition. Okay, I want all the attributes with the shared name to match, but you can generalize that to define different conditions. So that gives us what we call the theta join, okay? Which if you do a theta join between R1 and R2 with the condition theta, what you are going to get is essentially you have R1 cross product R2, and then you subselect all the tuples in the cross product that satisfy theta. So I see someone raised the hand. Yeah, so is there any questions?
Yeah, so there's a question in the chat, which is quite interesting. So what if so we're talking about like the natural join, what if the two joined tables share more than one attribute, but not all of them? Yeah.
Oh, yeah. So so if two relations share a subset of attributes, then I'm going to match all of them. Does that make sense?
So does that mean that not so all of them have to match, like not all?
Yeah.
Okay.
Yeah.
Okay.
Yeah. So you can think about B here as a subset of attributes.
Ah, okay.
Yeah. So everything in that subset need to match. Make sense? Okay, great. So yeah, so if you have any question, just raise your hand. So I won't be able to see the chat window because there are too many messages and yeah. So like whenever I have a question, raise your hand so I can see something pop up like in my screen, and I will switch to you and answer them. Okay. Okay, cool. There's another question. Yeah, go ahead.
So question, when we have no shared attributes, wouldn't it be the empty set? Like, because we only take the attributes that are the same.
Oh, yeah. So that's a so that's a very good question. So like here, right? So we'll go back to the definition here, right? So essentially, I do not have shared attributes. So essentially, like this one will not filter out any of the tuples, right? So essentially, I'm comparing an empty set with an empty set.
Yeah.
Yeah. So it's always so it's always the same because they're empty, right? So they're equally empty, right? So so essentially, like for every single tuple in the cross product, it will satisfy this condition. because I have nothing to compare with.
Okay, yeah.
Right? Yeah, I know it's very confusing. That's why this corner case is very important, because that can actually force you to actually think about like what are we really trying to do, right? We are trying to find like the matches, but if you ask me to compare empty set to empty set, that's empty, right? So yeah, that's the same. Right?
And another question, when you did the example with the Cartesian product,
yeah,
where we had two of the attributes were with the same name, and then you renamed them to like CID1 and CID2. Is that automatically, or do you have to rename them?
Oh, sorry. Yeah. So that will not happen automatically. Yeah, you need to rename them before it. Yeah.
Okay. Thank you.
Yeah. Sorry. Yeah. Thank you. Okay. So another question.
At the same slide, when you rename the CIDs, because the set is not does not care about sorting, how does the program know which one of the CIDs to rename into what?
Oh yeah. Oh, sorry. Okay, so I'm going to refine the slide to make that clear. So essentially here, I'm assuming that before the cross product, you are renaming the CID in customer to CID1, renaming this one to CID2.
So we'd actually get an error if we did it that way, the other way.
If you have a compiler for relation model, yes, you are going to get an error. Yeah.
Okay, thank you.
So in database, okay, so in real world database, it will let it run. Yeah, but if you talk about theory, yes, we are going to get error. Yeah, so I will refine this slide. Sorry. Yeah. Okay, so other questions? Yeah, let's go ahead.
If you could quickly switch to the renaming slide.
Yeah.
Since we said attributes are a set and not a tuple, how does the renaming guarantee that PID is renamed to A, CID to B, and stored to C, and not some other?
Oh, that's a good question. Yeah, so here I'm abusing the notation a little bit. I'm essentially like row PID equals to A, CID equals to B, store equals to C.
Oh, okay, all right.
Yeah, so you need to specify the mapping. Yeah, so that's a very good question. So like when I talk about the tuple, I think I always abuse the notation to kind of to avoid from writing the full name. But here essentially what happens really PID equals A. Yeah. Okay. Perfect. So any other questions? Yeah, just go ahead.
I'm just going to go ahead then. If you go back to the natural join, I think it was, we have or maybe is this one? The example, is there an example for this? Because if we do the cross product between R1 and R2 and they share B, in the table, we're going to have, we have the same attribute twice with different values. Doesn't that cause like a problem or something? Because when we refer to like, it's like, so we have the same attribute with the same name, but potentially different values. So when we say, okay, we want attribute CID, for example, like where does it, like, how does the system know which CID we are referring to?
Yeah, so that's a very good question. So yeah, so here if you think about this, so essentially I'm abusing notation a little bit. I'm saying that like the B come from R1, the B come from R2.
Okay.
These two need to match, right? So yes, so like you should do the, so essentially like, okay, so if you do not want that to happen, like at the end, you should do the renaming of the attribute in customer, you should do the renaming of attribute in purchase, and you do this.
Okay, that makes sense. Thanks.
Yeah, that makes sense, right? So and on the other hand, right? So for natural join, because my condition is these two should match, right? In the projection, it doesn't matter which one, like it doesn't really matter from which relation it comes from, right? So like essentially when I'm doing natural join, right? So I don't need to do the renaming before I do natural join, because at the end of the day, I'm going to do the projection on one of the B, and it doesn't really matter which B it is because I'm always saying they're the same, right? So, but you really want to write this expression in a very rigorous way, you need to kind of rename the R1's B into R1.B. You need to rename R2's B into R2.B. And then when you do the projection, you need to do maybe project to R1.B, something like that. Yeah. Okay.
Okay, thanks.
Yeah. But from user perspective, right? So you do not need to rename this before natural join because it doesn't matter like which B, like from which relation you pick the B, yeah. Especially for natural join. Yeah. Okay, so is there any other questions? Okay, so yeah, so just go ahead. So like essentially, whenever you have a question, just raise your hand. Sorry, I cannot go through all the chat like in real time because there are too many of those. Yeah, okay. I don't know why I mute myself. Yeah. Okay, cool. Where were we? Okay, so we were talking about the theta join, right? So this is actually you can specify one condition here, and you actually check whether it's true or not, right? So and then there's different type of theta join, right? You can check whether two conditions are the same or not. Sorry, like whether two attributes are the same or not, right? That give you equijoin. And there are multiple joins. There's outer join, and we are going to see it later, maybe next week, because we need to understand different. Yeah, we need to introduce a different concept before we talk about it, right? So yeah, so this is kind of all the operators you can do. We talk about operators that you can do on single relation, and we talk about operators that you can do maybe between two relations. When you query the database instance with relational algebra, right? So you can actually compose multiple operations together. And that's the beauty of it. And that's actually why it's an algebra system. That is, every single operator is going to take as input a set of relation instance, output a new one, right? So, and then you can actually stack multiple of those together, right, to do something more complex. So for example, if I have my database instance with these three relations, right, and I will say, okay, I want to find the customers who brought iPhone, right? So, and then what should I do? Right? I could write a query that look like this, right? So essentially, I say, okay, I first do the natural join between customer and the purchase, right? So essentially, I want to get all the product ID that this customer purchases, and then I will join this result with the product table, which is also a natural join, right? I'm going to subselect the result and only keep those with product name equals to iPhone, right? I'm going to project the result and only keeping the customer ID because that's what I want. So if you give me the expression like this, so what's going to happen is, okay, I'm going to first do the natural join here. My output is still a relation instance. I'm going to join that together with product. I'm going to do the selection. So I'm going to do the selection. I'm going to do the projection, right? So the only reason you are able to do it is that the output of each intermediate node is also a relation instance, and that's why you can actually stack them together. Okay, so let's look at another example, which is going to give us an operator that's actually pretty interesting. That goes beyond like what we learned so far. So think about this example. So I have two relations. I have a lecture relation, and I have attendance, right? So which is student ID, attend lecture. I then assume that my query is, I want to find students who took all lectures, okay? So how can we do that? So we already have the tool to answer that question, okay? That's going to be a very long expression, but we know what to do, right? So let's find all the students, right? So essentially I can project the attendance relation by only keeping the student ID column, right? Then I get all my students. I can do a cross product between all the students and all the lectures. And then I calculate the difference between that and attendance, right? So this gives you essentially all the missing lectures, all the student and lecture pair in which the student didn't take that lecture, okay? And then I can subselect the missing lecture relation on the student ID. Then I can find all the students who miss at least one lecture. And then I can calculate the difference between all students and the student with at least one missing lecture. Then I can get essentially the students who took all the lectures, right? So, I mean, if my query is find me all the students who took all the lectures, this is just one way that you can do it, right? So there's one operator that we can actually use to do a kind of to do this in a much shorter way, right? And that is one operator called relational division. Okay, so there's one operator you can do. You can say, okay, so attendance divided by lecture is actually exactly the answer of this query. And we are going to look at like this operator. So why do we call that division, right? So if you think about this, we need to go back to what is really division, right? So division is the inverse of multiplication. And here, when we are talking about relations, the multiplication is cross product. So essentially, we are trying to define kind of an inverse operator for multiplication or cross product in this case. So here's the formal semantic. So we say the result of like T is a result of R divided by S. If and only if T is the largest relation such that S cross product T is a subset of R. So this is actually how we define relational division. If you look at it, it actually makes sense, right? So very similar to the division of numbers, but the only difference is here we want to find T that's kind of largest relation, okay? And you can actually write it down, and then you can have something like this. This is actually very similar how we kind of answer the previous query, find all the students who took all the lectures, right? So like if you go home, it's very simple to prove that these two are equivalent. Okay. Yeah. So I see there are some questions. Yeah. Any questions? If there's a question, just go ahead. I saw someone raised hand.
I had a question, but I resolved it all good.
Okay, cool. Yeah. Okay, great. So that's division. So there are other operators that are kind of interesting. So one very interesting operator is semi-join. You are going to see it maybe in the last week of the course. We are going to use it again, but remember that. Yeah. So we see there's semi-join between R1 and R2, and that operation defined as follows. Okay. So I'm going to have R1 with all the attributes A1 to AN, and I have R2 with attribute B1 to BM. Okay. So when I do the semi-join with condition C, I'm pretty much essentially doing a theta join between R1 and R2, and I project that to all the attributes of R1. That's essentially like what I'm trying to do. Okay. So essentially, like that's why we have this type of kind of symbols, right? So essentially, I only want all the columns attributes from R1. I don't want those from R2, but I want to do the join first. I want to find all the result in R1 that would appear in the result of R1 theta join R2. That's what I'm trying to do. Okay. So if you think about why this is useful, right? So it's very useful when you are building a distributed database system. So there's a one optimization or one trick called semi-join reduction that's going to use this operator. So here's actually what will happen. Assuming that you are building a distributed database system, that different relations are actually stored on different machines. I have one relation with attribute A and B. I have another relation with attribute B and C, and I have two machines. On machine 1, I have R. On machine 2, I have S. Okay. So and then I want to calculate R join S. Here maybe let's assume I want to do natural join, like R join S. And the bottleneck of the system is the communication. I want to decrease how much information I need to send from one machine to the other. So how can we do this, right? So I mean, I could just transfer the whole R in from machine 1 to machine B. Sorry, like from machine 1 to machine 2, and then on machine 2 I have both R and S, and then I can just do the natural join. I could do that. if you calculate the communication overhead, that's going to be as large as R or as large as S, depending on the direction of the communication. Essentially, you are bounded by the smallest relation between R and S. If you want to transfer the full relation from machine 1 to machine 2 or machine 2 to machine 1, whatever. So one thing that semi-join comes into handy is that actually you can prove if you do the net join between R and S, it's actually equivalent to you first do R and semi-join with S projected on B on the shared attributes, and then you kind of join this kind of semi-join result with S. Okay, so this is very easy to prove, but let's think about why that could be useful. It could be useful is that to calculate the projection of S onto B, I don't need to communicate, right? So I can do that locally on machine 2 that hold the whole S. Once I get that, the result of this is going to be much smaller compared with S because that's a projection. And I'm going to send that result from machine 2 to machine 1, and then I can do the semi-join on machine 1 with R, okay? And then because the semi-join, right? So I only do the projection on the information like on all the attributes of R. And then I can send this information from machine 1 to machine 2, right? So that's essentially what you are trying to do with semi-join reduction. When you do the semi-join, you are trying to find all the information in R that matters for the join between R and S, because not all the information in R matters in the join. And if those information doesn't matter, they will not show up in the semi-join result. And then you do not need to send that from machine 1 to machine 2, because even if I send that, even if I communicate it, it will not be useful for my join. So this is a very interesting trick called semi-join reduction when you are building distributed systems. Okay, so now let's look at some examples. So let's take this one as our database instance. This is the university database that we have been building this lecture. Let's try to answer the query that I want to find all students who took database. Okay. So what type of like which relation do we need to care about? Okay. We need to care about the student relation. We need to care about the lecture relation, contains all the lecture information. We need to care about the attendance relation. Okay. So essentially, to answer this query, I need to do the natural join between student, attend, and then lecture, right? So if I do the first one, I'm going to have a relation look like this. Pretty much I have the student relation, right? And then I just put one more column here, which is the lecture ID, right? So then I know which student took which lecture. And then I join this one with the lecture table, which pretty much for each lecture ID, I kind of, you can think about that as expanded by the information of each lecture, right? And then I do the selection. I select all the lecture with title equals to database, and I project that to student ID, the personnel number. And then I get something look like this. So this is the query, right? What is a query? It's a function that takes as input a whole bunch of relation instance and output a new relation instance. Okay, so in this case, my query looks like this. This very long expression, which is going to take as input this database instance and give you a new relation. Okay, makes sense, right? So we can do a whole bunch of really powerful things here, right? So yeah, so I think we have one question. Go ahead.
Yes, so there's two questions in the chat. So one of them is, what's the associativity for the join operator? So I think the question is if it's left or right associative.
Oh, that's a very good question. I'm going to answer that in the next lecture. I'm going to talk about that in like for 20 minutes. Yeah, don't worry. Yeah, so that will come clear the coming Wednesday. Yeah.
Okay, and the other question is that am I correct in assuming pi is for the key and sigma the condition, and it's like a bit unclear on like what is like how it exactly works. I think the projection and the
Oh, yeah. Pi is projection. Theta is selection. Selection is you want to find a subset of rows. Okay. Projection is you project that to a subset of columns or attributes. That's the difference. Make sense? Okay, great. Okay, so yeah, so this is just one example, right? So when you go back home, right? So you can actually go through a whole bunch of different examples, right? Which is kind of pretty interesting. I put 2 examples here, and there are actually more examples in the book. Okay. So that's it. So let's recap. So this is the first query language that we have been looking at, relational algebra. Okay. It's not declarative. If you think about why, there are actually different ways to implement the same query, right? For example, if you want to find all students who take database, I could write something like this. I just do the natural join, right? So, but another thing I could just don't do natural join between student lecture, right? I just do the cross product, okay? And then I use the cross product result to do natural join with the terms, and then I do the subselection. This is going to give me the same thing, okay? But as you can see, this cross product is going to become very, very large. If you have a system that follows this expression, the second way of implementing the same query going to be much, much more expensive compared with the first one. And that's what we mean by the whole thing is not declarative, right? So there are so many different ways. I'm actually telling the database how to get the answer for me. But the downside of doing that is the database can only do what you tell it to do, right? If you doesn't give a good query to the database, it's going to be very, very slow. That's actually one thing we do not like about the relational algebra, because in the eye of the user, it's not really something declarative. So in real world database systems, users actually do not write relational algebra, right? So we actually hope to have a query language in which the user doesn't need to worry about different implementations, right? Because which implementation is the best is not only a function about the semantic of the query, but also the distribution of your data. If you ask a human to do that, that's almost set your user up to failure. It's very difficult to do. We want to have a query language that is declarative, kind of tell the database at high level what I want instead of how to get it there. And that is our goal. And that is actually something you are going to write in a real database system. So that's all for today's lecture. So in the next lecture, we are going to go a little bit even deeper about relational algebra, right? About the property of different operators. And we are going to see how in some other type of system, you are able to do some relational algebra there. We are going to go talk a little bit about pandas, about data frame, right? About how this can actually play a role even beyond database. And then we are going to talk about the second query language, that is relational calculus, which is a declarative query language with a very, very solid foundation of mathematical logic. Okay, so that's all for today. If you have any questions, I'll be here to answer it. Otherwise, I'll see you on Wednesday. Thank you. Yeah, go ahead.
Thank you very much. It was a pleasure.
Yeah, so for the natural join, did I understand this correctly, that it joins all of like if there are multiple attributes with the same name, it joins on all of those attributes? Like they both
yes.
have to match?
Yes, they both have to match. Yeah.
And if we want to match on like if we want to join on only one attribute, we need to use the theta join.
Exactly. Yeah.
Okay, thank you.
Yeah.
Could you quickly repeat why? So how you can remember the edge cases of the natural join?
Sure, of course. Let me go back to the slides. Yeah, so just give me a minute. Oh, here, okay. Cool. Which corner case are we talking about?
Actually, both, but let's start with the first.
Sure. Okay. Okay. So like in this case, right? So there's no shared attributes, right? So and then if you think about like what would happen in the theta part, I'm actually comparing two empty sets. So I will not filter out anything, right? So I'm going to essentially pipe the whole kind of cross product to the next operator. And this theta will not eliminate any other tuples, right?
Oh, okay.
Makes sense?
Okay, now I understand it. And yeah, the second case is trivial. Sorry.
Yeah. Cool. Okay.
Okay. Thank you very much. Have a nice day.
Sure. You too.
Could you understand? Could you explain one more time the semi-join?
Sure, of course. Yeah, I know. Yeah, so that part is a little bit confusing. Let me go to that. Okay, so which part? So you mean the definition, or you mean how we are going to use it and how we could use it?
Both.
Okay. Okay. So I'll semi-join. So with the condition C, right? So essentially, what you are going to do is you do the theta join between R1 and R2, and then you project to the attributes only of R1. So here R1 is A1 to AN, R2 is B1 to BM. Okay. When you do the projection of the join, you only pick those attributes in R1. Is this clear? So for example, right? So I want to do customer theta join purchase. Okay. So what would I have? Sorry, let's bring that here. Where is that? Sorry, too many slides. Give me a minute. Sorry. Okay, natural join. Okay, so if I do the customer natural join purchase, this is what I get, right? So if I do the semi-join, okay, with this direction, okay, if I do a semi-join, I would only keep these three attributes. I would have a relation with 2 rows and 3 columns. Make sense?
Wait, why? What? Why is that?
Oh, yeah. So, okay. So let me just give me a minute. So let me bring this. Okay. So you can see the text window, right? That I'm typing. Okay, cool. So essentially we'll talk about the join, right? So essentially, when I join these two relation, I don't know how to type semi-join, to be honest. Okay, so let's assume this is what we have. Let's do this. So when I do this, so what I'm actually trying to do is I will first join R and S. Okay. I do this, and then I project that to all the attributes of R. So essentially, this is what I'm trying to do. So like this is clear, right?
Yes. Okay. Yes, this is clear.
Okay. So now we talk about this very concrete case. Customer semi-join. Again, I don't know how to type semi-join. Tech with purchase. Okay. So simply I want to do this. So again, so I join this two, right? So I first join this two, then I get this table, right?
Yes.
Okay. And then when I do the projection, right? I only project the result to the attribute of customer, which is CID, name, and city.
Okay. Yes. That's clear.
Right. So the consequence of this is I'm only keep these 3 columns. Right.
Yes. This is this.
Yeah. So and if you think about why that could be interesting is, it essentially means The third column here, Kevin, doesn't really matter for the join, right? Kevin will not find a match in the purchase table in the join. So if I'm building a distributed database where one machine is holding customer, another machine is holding purchase, when I try to communicate between A and between these two machines, I do not need to send Kevin from machine 1 to machine 2 because it doesn't really matter to me. That is what we are trying to achieve. Does that make sense?
Yes. Okay.
Perfect. Okay. Great. Any other questions? Okay, so if there's no other question, I'll see you guys on Wednesday. Yeah. Bye.